Okay, so the next step is to summarize all your variables. So R has a function called summary. You just have to put the data set in and it will give you a summary of all of the different variables. And so it's quite smart, and it knows if you have a continuous variable, it will give you summary stats, it will give you the minimum, maximum, mean, median. If you have a kind of grouped variable, which is kind of a 0 or a 1, like male and female, it gives you the number in each group. So for AD here, obviously this is coded as an integer number, so they're either 0s or 1s. And so you might want to change the coding to be more like gender, so you get the numbers. But it does give you, the mean is 0.3, which is the proportion of cases, which is quite interesting to know. And so similarly, you have this across all of them. For smoking status, you have 3 groups. It's given you the number in each of the groups.
So the summary function is working based on columns?
Yes. Yeah, so it summarizes each column in your data. And so you can see it even summarizes your ID column, which is obviously just a number for each row. And then the second one is to make a contingency table. So this is just a 2x2 table to find out the number of people who have AD and high blood pressure, the number of people who don't have AD and don't have high blood pressure, and then also the other groups in between. So similar to the odds ratio tables we looked at earlier. So R has this table function, and because AD and high blood pressure are coded as 0 and 1, so 0 if they don't have AD, 1 if they do, that's why you get these labels here. But you can add labels to this as well. And then finally, if you want to do a scatter plot of BMI against age, and so you should get something that looks a bit like this. So you can see there's not really anything particularly interesting in this data because it's randomly generated. And there's many packages in R to do kind of fancier plots, but these are just to show you how to do some standard plots, just so you know how to do it.
So for that plot, so if it is interesting, we should find this trend, see trend or something like there's a correlation or something?
Yeah, so if age was to differ with BMI, you might expect to see like the points kind of cluster in a particular direction, but here they're random, so as BMI increases, the age is kind of consistent, but you might see like a particular trend in some cases. The summary function is also quite good to pick out outliers, which is something I'm going to talk about in a bit. So you might have noticed for age, your minimum value is negative. Obviously, this is probably a mistake. You wouldn't expect someone to have a negative age. And so this function can be very useful at picking out those things. Okay, so the next step is to do another scatter plot, but make it slightly more complicated. So this time it's the same plot, but you're changing the colour based on whether or not someone has Alzheimer's disease, and you're also adding a legend. And so you can use this part here, which subsets the data. So you're saying you want to plot BMI where AD is equal to 0. And so it splits them. And so the first one is black, and the second one you're colouring red, so you can see that it's the AD cases that are in red. This is just plotting histograms, but in the interest of time, I'm going to skip it. So data quality control is something that's quite important. As you were doing those last plots, if you managed to get them done, you might have noticed that there were some outliers in your data. So I don't know if anyone noticed that there was someone who had an age of negative 67, which is obviously a mistake. So that's why plotting your data before you do anything is incredibly important, because you can spot things like that. You can spot data that is either a mistake or data that it could truly be an extreme value. And so you then have to decide whether you want to correct it or whether you keep it in because it could actually be a real value. The other thing that you need to consider is missing data. If you have a variable that has the majority of entries is missing, then you start to question how good the quality of that variable is and whether you actually want to be basing any analyses on this variable. And there's different things you can do with missing data. You can either just remove it completely. So if you have the odd bit of missing data, removing it isn't really a big issue. But if you have a huge number across all different variables, then you can impute your data. And so this is, you kind of take an average value based on other individuals who are similar. So if you were missing an age variable, you could look at sex and you could look at all of the other variables you have, find someone who's similar in all of those other variables, and then you would guess what their age is based on everything else.
But again, there is a software which will do it for you, so it's not you who decided.
Yeah.
There is a software, it's not for this practical. If you're interested, you tell us later what kind of practicals you would like to have, and we can adjust it for future.
Mm-hmm. And so I'm going to go on to regression because I think this is quite important. So regression is a very simple method and it's very robust. It's used to model the relationship between two variables. So you have your dependent variable y and your independent variable x, and you form an equation. And there are different types of regression depending on what your variable y looks like. So if it's a continuous variable, so something like systolic blood pressure, you would use linear regression. Whereas if your dependent variable is binary, so if it's case control status, you would use logistic regression. And I'll talk about why you use these different methods in a second. And so some more formula for you, but hopefully I'll explain them well enough. So y is your dependent variable, so this is the thing that you're interested in modelling. X is your independent variable, and so you want to see if changes in x affect y. Beta naught is your intercept, so this is where your equation crosses the y-axis. I'll show you this in a plot in a second. And beta 1 is the slope, so how steep your association is, and it can be positive or negative. And then this is your error term. Again, I'll show you what this is. And so going back to your hypothesis testing, when you're looking at regression, the null hypothesis is that the slope is 0, so it's that you have a horizontal line, and then your alternative is just that it's non-zero. And so this is kind of what it would look like. So this solid line here is your regression line. These kind of crosses are your points. And so beta naught is the intercept. So this is, as I said, where your regression line crosses the y-axis. Beta 1 is how steep this line is. It can be negative, so it can be in this direction as well. Your error is the distance between the regression line and each of these points. And as I said, the null hypothesis is when your slope is 0, so it's when you have a completely horizontal line. And so what that means is that y doesn't change whatever value of x. And so that's your null hypothesis that you're testing. And so, as we mentioned right at the beginning, the important with statistical tests, you need to think about what assumptions underlie that test to see if it's actually valid for your data. And so these are the assumptions for linear regression. And so you need the mean of the residuals to be 0, the variance of the residuals to be constant, and they should be normally distributed. And you also want two observations to be independent. So independence is something that you know about your data. If they're all individuals who are unrelated and they're collected separately, then it's independent. The other things I will show you, you can test just by doing a couple of plots, and you can see what they're supposed to look like. So I've shown you simple linear regression. This is multivariable linear regression. So when you have lots of variables that you want to include. So for instance, if you just want to adjust for things like age and sex, you can include those in your model as extra independent variables. And so the global hypothesis for this is that none of these betas, so the global null is that all of these betas are 0, and then the alternative is that at least one of them is non-zero. But when you actually look at the output, you'll see you get a p-value for each of them, so you get kind of a local hypothesis, which is testing each of these betas separately. This is just how you run a simple linear regression in R. So you use this GLM function, and this family equals Gaussian. This is what's saying that it's linear regression rather than something else.
So if you now type this command in your computer, that should give you...
Yeah, you should basically get this output. And so I'll talk through a little bit how to interpret this. Based on the equation that I showed you earlier, these are the kind of values. This table here is what you're most interested in. And so this estimate here, the intercept, this is your beta 0. So this is where it crosses the y-axis. People tend to ignore this one, so it's not too important, but it's just useful to know that that's what the number is. This estimate here, this 0.467, this is your beta 1. So this is the association between BMI and systolic blood pressure. And then this value at the end here is your p-value. So you can see that it's 0.19. So if you were basing it on a significance level of 0.05, it would not be significant. But if you had a significant result and you wanted to interpret this value, what it means is if your BMI goes up by 1, then your systolic blood pressure would go up by 0.467. So that's how you would interpret this value. And so as I said, you have assumptions for your model, and so the next step is to test them, but I'll kind of So you need the model residuals and the fitted values. The fitted values are just the y values for your regression line. And so R has a function that will tell you what these are. And you can have a look at them, and this is kind of what they look like. And so if you plot a histogram of the residuals, you'll see it kind of has this normalish shape. So this is okay. And so the residuals need to follow a normal distribution. So you can check this, and here they look fine. And the other assumption was that the residuals have constant variance. And so you can see there's no particular trend here. It's just kind of a random scatter about 0. And so that's kind of what you want. So the assumptions in this case are fine. So this is an example of, so this is plotting your systolic blood pressure points against BMI and then fitting the regression line. So this red line here is your regression line. So you can kind of see why you didn't get a significant result because it's almost horizontal. And then, as I said, you can add extra variables into the model. So this is the formula here. You just add and then put the names of all of the independent variables you want to include. And then in your output, you'll have extra rows. So here you'll have age and sex as well. And so you have p-values for both of those and effect sizes here. And so looking at BMI again, it's not significant because it's the same data. And so here you can see this number's changed slightly. And so what this means is that if BMI goes up by 1 in someone that's the same age and the same sex, you'd expect systolic blood pressure to go up by 0.47.
Because you included another variable, then the calculation would count these other factors in.
Yes, so this is now adjusted for, so it's assuming that the people are the same age and the same sex. So it's the difference assuming that they're the same. So I said I was going to touch on logistic regression. So if your dependent variable is binary, so if it's a yes-no case control, 0 or 1, then linear regression is no longer appropriate. Logistic regression predicts the probability of an individual being in the 1 group or the case group, for example. So you can't use linear regression because linear regression, there's no limits on the values that it can predict. And obviously you can't have a probability that's not between 0 and 1. And so that's why it wouldn't work. And also you don't often have a linear relationship. And so you can see you normally have this kind of dose-response curve. And so that's why you can't use linear regression. So it's important to think.
Regression, there's no limit for the numbers.
No, for logistic, you have limit for the numbers. For linear, you don't.
Yes. So yeah, because logistic regression, you have a binary variable, so it's zeros and ones. Obviously, if you had a value of 100, it doesn't mean anything. And so another formula, so this is very similar. It's just your dependent variable is now different. So it's based on the probability of being a case or being in the 1 group. And then all of the other terms are the same, except here. So beta 1 is now a log odds ratio rather than just a increase. And again, you can do multivariable logistic regression and include other independent variables in your model if you need to. So again, an example of this, so a simple logistic regression model of Alzheimer's disease against age. And you can see, so again, you've got your estimates here. So these are your log odds ratios. So again, this is beta 0 and this is beta 1, but these are log odds ratios now. And your p-values for them, again, it's non-significant, which is Alzheimer's and age, you would expect it to be, but this is made-up data. And so this is your log odds ratios can be quite difficult to interpret, and people they're used to seeing odds ratios. And so if you want to see what it is in an odds ratio, you can just take the exponent of the log odds ratio. So the exponent and log are basically like plus and minus, they're the opposite of each other. So by taking the exponent, you're taking it back to an odds ratio. But yeah, so if you take the exponent, you get an odds ratio less than 1. It's obviously very close to 1, so this is why you have a non-significant value. So this is actually saying that if your age increases, your odds of Alzheimer's goes down, which obviously doesn't make sense, but this is made up data and it's a non-significant result anyway, so it can vary randomly about 1. And then the, I think, final example is just doing a multivariable logistic regression. So again, the same as before, you now have extra rows, and again, you've adjusted for those other variables in your estimates.